Swayam Prabha. Digital India. Educated India.
Hello student, welcome back. So, in the last class we have solved several linear problems using simplex method. I hope now you are familiar with simplex method and you can handle a linear problem using simplex method. So, today's class I will solve two new problems, and initially I will formulate the problem, and then one problem I will solve using simplex method, and another problem I will show you graphically and how you can find out the optimal solution of the problem, and then I will solve these two problems using Excel solver. So, I will basically show you how you can apply Excel solver for solving a linear problem. So, let us see the first problem. So, I can say it is example 5. So, we have solved up to example 4 in the last class. So, this is example 5. The problem is a manufacturer produces A, B, C, D. So, these are some of the items by using two types of machines. One is lathe and another one is milling machine. The time required on the two machines to manufacture one unit of each of the 4 products, the profit per unit products, and the total times available on the two types of machine per day are given below. Okay. So, this table has given the data. So, there are 4 products, as you know, that A, B, C and D. If we produce these products on the lathe machine, then time required per unit, that is in minute for the product, is 7 minutes. That means, one product will take around 7 minutes in the lathe machine, and that is for product A, and product B it will be 10 minutes, then product C 4 minutes, and product D 9 minutes. So, if you are producing A, B, C, D on the lathe machine, then 7 minutes will be taken by product A, then 10 minutes by product B, then 4 by product C and 9 minutes by product D. Now, the total available time. So, this much time I am getting, actually the lathe machine is available for 1200 minutes. The same product A, if we are using the milling machine, then time required is 3 minutes for product A, then 40 minutes for product B, then 1 minute for product C and 1 minute for product D. Now, what is the profit we can earn? The profit for product A is 45, then product B is 100, then product C is 30 and product D is 50. So, now what we have to do? We have to formulate an optimization model. Okay. Okay. Before that, the time available in the milling machine is 800. That means, 800 minutes I can use this particular machine. Okay. Milling machine I can use for 800 minutes. Now, what is the question here? The question here is that I have to formulate an optimization problem, and what we have to do? We have to maximize the profit. Okay. So, maximize the profit. So, we have to schedule our things in such a way that we can obtain the maximum profit. So, now let us formulate the problem first, and then I will solve this problem using simplex method, and then I will show you how you can solve this problem using Excel solver. So, the question is the find the number of units to be manufactured for each product per day for maximizing profit. The question is that we have to maximize the profit. So, we have to do the scheduling and we have to find out so that we can earn or we can achieve maximum profit. Now, let us take the variable. So, we have the x1. So, x1 is the number of units of A. Okay. So, I would like to produce x1 unit of A, then x2 is the number of unit B, x3 is C and x4 is D. So, number of unit of D. Okay. Now, let us see what is the optimization model. So, here the objective function is maximization type. What is that? I would like to maximize the benefit. Okay. Now, if I produce x1 of A, then per unit benefit is 45 unit actually. So, it may be in rupees or it may be in some other unit. So, 45. So, therefore, total benefit you are earning from the product A is 45 x1, then product B is 100 x2, then product C is 30 x3 and product D is 50 x4. Okay. So, this is the benefit we are earning. So, therefore, the objective function is maximize this benefit. Now, what are the constraints? So, the lathe machine is available for 1 to 00 minute. So, therefore, if I produce x1 of A, then how much minutes I need? I need 7 minutes. Okay. So, therefore, the 7 into x1 is the total time required in the lathe machine for producing x unit of A. Similarly, the total time required for B in the lathe machine is 10 x2, then for C 4 x3 and for D that is 9 x4. Okay. And summation of all these things should be less than 1200. So, that is the available time. That means, I cannot use the lathe machine more than 1 to 00 minute, 1200 minute. Similarly, if I use the milling machine, then total time required for product A is thrice x1, then product B is 40 x2, product C is x3, 1 into x3 and product D 1 into x4 and the total time should be less than 800 minutes. Okay. So, I have total 800 minutes and this x I should be greater than or equal to 0. So, I equal to 1 to 4. Okay. So, now altogether this is an linear problem. So, I have formulated the linear problem. So, objective function is maximization type function because I would like to maximize the profit and I am putting the constraint. What is constraint? The time availability on the lathe machine as well as milling machine. Now, what is the next step? So, I think already you have solved several problems. So, what you have to do basically, we have to convert this problem to standard form. So, the first one is that I would like to convert it to minimization type. So, how I am converting? So, I am multiplying the objective function by -1. So, therefore, I am getting minus 45 x1 minus 100 x2 minus 30 x3 and minus 50 x4. And the constraints, so constraints are that is 7 x1 plus 10 x2 plus 4 x3 plus 9 x4. Now, I am putting a slack variable here, this is x5 just to make it equal and this is equal to 1200 and similarly on the second constraint. So, I am putting another slack variable that is x6 which is equal to now 800. So, just to make it 800. So, now with this standard form now I have x5 and x6. Okay. So, I can get the initial basic feasible solution if I put x1 2 x4 0, if I say that these are non basic variable and x5 and x6 are basic variables. and in that case, so I can obtain an initial basic feasible solution, which is x 5 equal to 1200 and x 6 equal to 800 and x 1, x 2, x 3, x 4 are 0. So, they are non basic variable. So, let us put at the simplex table. So, we have this is x 1, x 2, x 3, x 4, x 5 and x 6. So, I am putting that constraint. So, this is 7 coefficient of x 1 in the first constraint is 7, then x 2 that is 10, 4, 9, 1 and this is 0 and this is 0 and which is equal to 1200, and the coefficient of x 1 in the second constraint, that is 3 for x 2 40, then 1, 1, 0, 1, 0 and finally, it is 800, and I am putting the objective function, and this is minus 45, coefficient of x 1 is minus 45, minus 100, minus 30, minus 50, then this is minus 1 and 0. Okay. Now, x 5 and x 6. So, x 5 and x 6 are now basic variables. Okay. So, they are basic variable x 5 and x 6, and x 1, x 2, x 3 and x 4 are non basic variable. Now, what is the first step? That I have to look at the objective function rho, and I have to look for the minimum value here, minimum negative. So, what is minimum negative here? That is 100. So, that is the minimum one. So, therefore, the x 2 will enter into the basis. Now, question is that which will come out of the basis, whether x 5 or x 6. So, I have to look at the b by a I j ratio, and this is 120, okay, that is 1200, that 1200 divided by 10. So, I am getting 120 and this is 800 divided by 40. So, I am getting 20. Okay. So, what I have to do here? I have to take the minimum one, that means 20. So, therefore, this is my pivoting element. So, what I will do? I will make this 1 and for others I will make it 0 and 0, something like that. Okay. So, if I do that, if I do the row operation, so finally I am getting this is 0, this is 1 and this is 0, and now I have to look at. So, you just see now x 2 is entering into the basis. So, x 2 is now basic variable and x 5 is also basic variable, and other variable that is x 1, x 3, x 4 and x 6, x 6 is now non basic variable. So, what is the solution now here? So, I can say that x 5 equal to 1000, x 2 equal to 20 and the objective function value is minus 2000. Now, what you have to check? Now, we have to check is there any negative coefficient on the objective function row? Yes. So, we have actually. So, this is minus 37.5, this is minus 27.5, this is minus 47.5. That means, I can still reduce the objective function value, and what I have to do? I have to take the minimum one. So, minimum one here is that 40 minus 47.5. So, therefore, x 4 will come into the basis. Now, whether x 4 will replace x 5 or x 2. So, let us look at the ratio here. The ratio here is that is 1000, okay, divided by 8.75. So, I am getting 114, and the second one is this is 20 divided by 0.025. Okay. So, I am getting 800. So, what I have to do? I have to take the minimum one. So, here minimum one is 114. So, therefore, this will be my pivoting element. So, I will make it 1 and for others I will make it 0. So, after that, so I am getting this table. So, now x 4 is entering into the basis and x2 is already there. Now, is there any negative coefficient on the objective function rho? Yes. So, we have minus 3.57 and this is minus 7.14. So, what I have to do? That means, we can still reduce the objective function value. So, therefore, I will consider the minimum negative. So, here it is minus 7.14. Let me calculate the B by A I J ratio. This is 266 and this is 1200. Okay. So, therefore, this is the minimum one. So, what you have to do? This will be the pivoting element. Okay. So, then let us go to the next table. So, in next table, so this is 1 and this is 0 and x 3 is entering into the basis. So, x 3 is now basic variable and x 4 is non basic variable. So, in this table, that if you look at the objective function rho and there is no negative coefficient, okay, all are positive. This is positive, 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 okay, and this is also positive. So, therefore, it is not possible to decrease or to reduce the objective function value. So, that means we got the optimal solution. So, what is the solution now? That x 1 as a non basic variable. So, that is 0, x 2 is a basic variable. So, which is equal to 13, okay. This is 13. Then x 3 is also a basic variable which is equal to 267, x 4 is a non basic variable 0, x 5 is non basic variable 0, x 6 is non basic variable 0 and what is the objective function value? Objective function value is minus 9333, that means 9333. So, that is the objective function value. Okay. So, the maximum benefit I can achieve is 9333 and what I have to do? That x 1 is 0 basically. So, I will not produce the A product A, I will produce only product B, that is x 2. How many unit? I will only produce product B of 13 units and product C of 267 units and product D is 0. So, what I will produce? Product A, there is no product A, product B 13 unit, product C 267 unit and product D 0 and maximum benefit I can achieve is 9333. So, we got the solution of this problem. So, I will also show you how you can solve this problem using Excel solver. So, before that, let us discuss the next problem. The next problem is problem 6. The problem is there are two sites, site A and site B, to extract sand and gravel raw materials for a construction project. So, what we can do? There are two sites. So, from site A and site B, so we can extract sand and gravel. So, sand and gravel that is required for a construction project. Okay. So, I can take either from site A or from site B or from both site A and site B. Now, due to variation in soil properties at each site, the raw materials from site A produces 30% of sand and 70% gravel. Okay. So, if I take the raw material from site A, that raw material contain 30% of sand and 70% of gravel. On the other hand, if I take the raw material from site B, so that produces 50% of sand and 50% of gravel. Okay. So, 50% sand I can get or 50% gravel I will get if I take the raw material from site B. The construction job or construction project requires a minimum of 35,000 cubic meter of sand and gravel mix. So, that is the requirement. So, sand and gravel mix requirement is the minimum 35,000 cubic meter. Okay. The minimum requirement of sand is 15,000 cubic meter. Okay. So, sand requirement is 15,000 cubic meter and the requirement of gravel is not more than 20,000 cubic meter. So, gravel requirement is less than 20,000 cubic meter, but sand requirement is more than 15,000 cubic meter. So, that means minimum requirement is 15,000 and but for gravel the maximum requirement is 20,000. The delivery cost per cubic meter of raw material are rupees 700 and rupees 800 from site A and site B respectively. That means, if I take 1 cubic meter of raw material from site A, the delivery cost is 700 and if I take it from site B, the delivery cost is 800. Okay. So, now we have to take a decision that how much raw material you are taking from site A and how much raw material you should take from site B in order to minimize the cost. Okay. So, here what is your objective? That objective is to minimize the delivery cost. Okay. So, that is my objective and now I have to take a decision that how much material you are taking from site A and how much material you are taking from site B. Okay. So, we have to formulate the problem and after that I will show you graphically how you can find out the solution of this problem and later on I will solve this problem using Excel solver. So, let us formulate the problem. So, here x 1 is the amount of material from site A, that means x 1 is the amount of material that raw material I am taking from site A. X 2 is the amount of material that raw material I am taking from site B. Now, what is the objective? Objective is to minimize the delivery cost or we can say transportation cost. Okay. So, therefore, the objective function is a minimization type, that means I would like to minimize the delivery cost. Okay. So, what is the delivery cost per cubic meter? That is 700 for site A. So, therefore, the total delivery cost will be 700 into x 1 and from site B that is 800. So, delivery cost for site B is 800 x 2. Okay. And I would like to minimize this particular objective function because I would like to minimize the delivery cost. The first constraint is that the sand and gravel mix should be more than 35,000 cubic meter. So, therefore, x 1 plus x 2, okay, that is the gravel and sand mix. So, x 1 plus x 2 should be greater than 35,000 cubic meter. Okay. So, that is one constraint, that the total gravel and sand mixer should be more than 35,000 cubic meter. Now, the total amount of sand should be more than 15,000, that means the minimum requirement of sand is 15,000 cubic meter. So, if I take sand, if I take the raw material from site A, then how much sand I am getting? The 0.3 x 1, and if I take raw material from site B, then how much sand I am getting? 0.5 x 2. So, therefore, 0.3 x 1 plus 0.5 x 2 should be greater than equal to 15,000, that is the minimum requirement of sand. Similarly, the maximum requirement of gravel is 20,000 cubic meter. So, if I take the raw material from site A, so how much gravel I am getting? 0.7 x 1, and similarly if I take the raw material from side B, how much gravel I am getting? 0.5 x 2. So, therefore, 0.7 x 1 plus 0.5 x 2 should be less than equal to 20,000, and x 1 and x 2 should be greater than equal to 0. So, these are the constraints. So, I am getting this particular linear problem. So, here objective function is a minimization type function. I would like to minimize the cost, and I am getting all 4 constraints, that is x 1 plus x 2 greater than 35,000, greater than equal to 35,000, then 0.3 x 1 plus 0.5 x 2 greater than equal to 15,000, and 0.7 x 1 plus 0.5 x 2 less than equal to 20,000. So, let us plot it. Okay. So, if I plot it, the blue line is basically that x 1 plus x 2 equal to 35,000, the blue line. So, therefore, it should be greater than means that the value should be on this particular side. Okay. So, I can say this is the value should be on this side. This is the constraint. The second constraint, that is 0.3 x 1 plus 0.5 x 2 equal to 15,000, and this is also greater than type. So, therefore, this is your feasible side. Okay. So, this is your feasible side. The solution should be on this side, Okay. And the third one is your this one, that is the third constraint. The third constraint is 0.7 x 1 plus 0.5 x 2 less than 20,000. So, therefore, this is the feasible direction, okay, feasible side. That means, solution should be on this side. So, you just see that whatever solution I should get, that solution should satisfy all these 3 constraints. So, in this case, if I see the solution is somewhere here, because if I take any solution here, this will be an infeasible solution, any solution on the other side, this will be an infeasible, here also it is infeasible, all solutions are infeasible, only this solution is a feasible solution, and which will satisfy all these constraints. Okay. So, if I look at the close view of this particular point, so you can see that this is the point where all these 3 constraints, or you can say 4 constraints, that is with non-negativity constraint. So, this is the point where it will satisfy. So, therefore, the solution is that x 1 will be 12,500 and x 2 will be 22,500. Okay. So, 500 cubic meter. That means, from site A, if I take 12,500 cubic meter, and side B if I take 22,500 cubic meter, and then whatever cost I will get, and that will be the minimum cost, and that will also satisfy all these constraints. So, therefore, this is the solution of this particular problem. Now, let us see how we can solve this problem using Excel solver. So, let us solve the problem 1. So, that is a maximization type problem. So, the objective function is f equal to 45 x 1 plus 100 x 2 plus 30 x 3 plus 50 x 4, and we have 2 constraints. Okay. To start the problem, so let us define the variable first. So, we have 4 variables here, that is x 1, x 2, x 3 and x 4, and I am putting some initial value in this cell. So, that is 0, 0, 0, 0, all are 0. So, I have defined the variables here. Okay. Now, let us define the objective function. Okay. So, objective function is f. Now, I have to write this equation, this objective function equation, and objective function is 45 x 1 plus 100 x 2 plus 30 x 3 plus 50 x 4. How I will write? That is 45 star x 1. So, this is the x 1 value, okay, plus 100 star x 2 plus 30 star x 3 plus 50 star x 4. So, I have written the objective function here. So, this cell is giving the objective function. So, I am just putting some color here maybe. So, this is my objective function. Now, I have to define the constraints. So, we have two constraints here, that is Z 1 and Z 1 equal to, that is 7 star x 1 plus 10 star x 2 plus 4 star x 3 plus 9 star x 4. Okay. So, I have defined here, that is 7 x 1 plus 10 x 2 plus 4 x 3 plus 9 x 4, and I can define here this is a less than equality type constraint and this must be less than equal to 1200. Okay. So, this is my G 1. So, I can say this is right hand side and this is left hand side, Okay. So, there is another constraint, that is Z 2. So, I am writing the left hand side. So, left hand side equal to 3 star x 1 plus 40 star x 2 plus x 3 plus x 4, and this is also less than equality type and this is equal to 800. So, now I have defined my constraints here. Now, let us solve the problem. So, for solving the problem, I have to use the Excel solver. So, Excel solver is your in data. So, you can see that solver should be somewhere here, and if it is not there, so you go to file, then go to option and go to add-ins. So, this is Excel add-ins you should get, and after that you just check solver add-ins and make it OK. So, then this solver will appear here. So, in my case already I have installed that one. So, I will not install it again. So, the solver is here. So, let us use this solver. So, you go to solver. Now, here I have to define the problem. The first is the objective function. So, objective function cell is here. So, this cell, that is D8 is the objective function cell. Now, my problem is the maximization type. So, therefore, here I can define either maximization, minimization or value of. Okay. But in my case this is a maximization problem. So, already maximization is checked. So, I use maximization. Then by changing the variable cell. So, these are my variable cells. So, I have to define, that is D3 to D6, okay, D3 to D6. So, I have defined my variable cell here, and then I have to add the constraints. So, constraint is that this is the first constraint, left hand side of the first constraint, and this is less than equal to, and this is the right hand side of the constraint. So, now I am adding it. Okay. The second one is, this is the left hand side of the constraint, and this is the less than equality type constraint, and right hand side is 800. Okay. So, I am defining this constraint. So, I have defined these two constraints here, and then I will use, so I have to change the setting here. So, I will use the simplex LP model. Okay. So, now my decision variables are non-negative. So, therefore, I have to check this particular box, and now I have defined everything. So, you can go to option and you can change the parameter here, but I will use the default parameter. So, I am not changing anything here. So, I can solve it. So, if I have defined my problem correctly, I should get the solution of the problem. So, let us solve it, just see if it is correct, then I will get the solution. Yes. So, solver results showing that solver found a solution, all constraints and optimality condition are satisfied. Okay. Now, let us go to answer. So, if I go to answer, then I should see the answer here. So, this is the answer report, and you can see that the objective function cell is now 9333. Okay. So, that is 9333. I already solved this problem using simplex method, and the maximum benefit you can earn is 9333. So, I got the solution, and the solutions are the x 1 equal to 0, x 2 equal to 13.33 and x 3 equal to 266.67. So, that is the solution already we got 13 and 267. Okay. So, and other x 4 equal to 0. So, x 1 equal to 0, x 2 equal to 13 and x 3 equal to 266.67, or you can say 267 unit. Okay. So, that means we got the solution of this particular problem. You can also see here that now x 1 equal to 0, x 2 equal to 13.33, x 3 equal to 266.67, and you got the solution here also. So, you can see that this is the solution of this problem, and here you can see that the left hand side is now 1200 and this is 800, and which is basically equal to less than equal to 1200 and 800. Okay. So, I can see the solution here also, or I can see the answer report. Now, let us solve the problem 2. So, this is problem 2, and this is a minimization type problem. Minimize f equal to 700 x 1 plus 800 x 2, and we have this constraint, 4 constraints. So, here also you define the variable. So, we have two variable here that is x 1 and x 2, and I would like to put an initial value of 0 and 0. So, this is, let us define the objective function. So, that is f equal to 700 star x 1 plus 800 star x 2. So, this is my objective function. So, let us define constraint. So, we have 3 constraints here, that is z 1 equal to x 1 plus x 2. So, you can say this is left hand side and this is right hand side. So, this is the left hand side is x 1 plus x 2, this is greater than equal to, this should be 35,000. Okay. Then z 2 equal to 0.3 star x 1 plus 0.5 star x 2, and this is greater than equal to 15,000 and Z3 equal to 0.7 star x1 plus 0.5 star x2, and this is less than equal to 20,000. So, I have defined the constraints here, all the constraints. Okay. So, G1, G2 and G3. So, I have defined here. Now, let us solve using Excel solver. So, you go to data, then use solver. So, here first you define the objective function. So, this is your objective function, and now this is a minimization type problem. So, therefore, you change it to minimization, and by changing these two cell, that is D3 and D4, and define the constraint here. The constraint, the first constraint is this is the left hand side of the first constraint, and this is greater than equality type. So, this is greater or equal to 35,000. So, you add it. Then this is the second constraint, left hand side. Now, it is also greater than equality type, and you define right hand side. Okay. I have another constraint. So, you go there, then this is the left hand side, and this is less than equality type, and right hand side is 20,000. So, you just see I have defined all these three constraints here. First one is greater than equality type, then this is also greater than equality type, and this one is less than equality type. Okay. So, now I will use simplex LP. Now, let us see if I have defined the problem correctly, I should get the solution. Yes. So, I am getting the solution. You just see that x1 equal to 12,500 and x2 equal to 22,500. Let us see the answer. The answer report shows that f equal to, this is the value of f, and then I am getting x1 equal to 12,500, x2 equal to 22,500, and you can see the all constraints are satisfied. Okay. So, you can see this is the all the three constraints are satisfied. The first constraint is greater than equal to 35,000, the second one is greater than equal to 15,000, and third one is less than equal to 20,000, and we got the solution, same problem you can see. So, this is the solution of this particular problem. You can see the solution is x1 equal to 12,500 and x2 equal to 22,500. And here also we got the solution that x1 equal to 12,500 and x2 equal to 22,500.